Hello, this is Tuhy, and for my semester project, I did a topology optimization of an aerospace tension tie in MATLAB. A tension tie is a structural component used in multiple industries and provides stiffness and stability under tensile loads. The idea for this project came from my work where the F-18 uses a tension tie to connect the left-hand and right-hand sides of the cockpit together and keeps the cockpit from bursting when pressurized. And we're currently redesigning to make room for more hardware. There have been several research papers and experiments on the optimization of strut and tie models in reinforced concrete. And this is a similar application of tension ties and shows the importance of having an optimized design because these components affect the overall fit, form, and function of the structure they're a part of. If they're too small or weak, they could fail and lead to a safety risk, and if they're too large or heavy, they could add extra weight or cost. For my project, I am investigating two uniform cross-sections, circular and rectangular, and we'll be optimizing the cross-section dimensions. The overall length is set to 30 inches, as this is the length to connect the left-hand and right-hand sides of the cockpit together. I'm also investigating three different materials commonly used in the aerospace industry: aluminum, titanium, and stainless steel. For the optimization, I am minimizing the volume of the tension tie, and the model is subject to three load constraints. The tie must withstand an axial load without yielding, an out-of-plane bending load, as well as a bearing load at the fastener holes used to attach the tie to the substructure of the cockpit. And the loads used for these constraints are representative of F-18 loads. I'm also constraining the width of the rectangular cross-section to maintain at least a 2 times diameter edge distance for the 1/4-inch fasteners. I'm also constraining the thickness of the tie due to the surrounding substructure. So these constraints are shown in standard format, and MATLAB will be used to solve for the optimized shapes using continuous variables. So from MATLAB, these are the results for each of the optimized cross-sections, circular and rectangular cross-section for each material. And with these, I calculated the cross-sectional area, volume, mass, and price of each tension tie. And then I normalized the rectangular results for easy comparison. So looking at these normalized values, we see that the aluminum would be the cheapest but largest tension tie, titanium would be the lightest but most expensive, and a steel tie would be the smallest but heaviest. So if I were to recommend one of these, I would first recommend using a rectangular cross-section because it provides a flat surface for fastener installation, and I would also value performance over price. So from this, I would recommend using a rectangular cross-section for the tension tie made of titanium. If I were to continue this work, it would be interesting to investigate variable cross-sections. This would allow more material at the max bending location or bearing stress location. I'd also investigate limiting the 2 times diameter edge distance to only near the fastener holes. This would essentially be a dog bone specimen shape commonly used in tension tie or tension experiments. This could provide an overall optimized volume better than a constant cross-section. Thank you.